My name is Connor. I'm the android sent by CyberLife. In this lecture, we're going to solve an action problem involving a block sliding on a moving inclined plane by using Lagrange equations. Throughout this video, I actually encourage you to solve the problem with me and fill out some of the algebra that I skip. I've mainly just skipped the simple stuff like isolating terms in an equation, but in any case, following along will be quite useful. And if you don't feel like following along right now, I've posted lecture notes in the description for you to review later. Suppose we have a block of mass m on an inclined plane or wedge of mass capital M. The angle of the wedge is alpha and the length of its inclined surface is L. The wedge is frictionless and it rests on a frictionless horizontal surface over which it's free to slide. Now here's the problem. If I start from rest and release the block from the top of the wedge, how long will it take the block to reach the bottom? So let's begin the problem by drawing everything out. We've got the wedge or inclined plane with angle alpha. L is the length of the inclined surface, and the mass m is found on top of that inclined surface. The wedge has mass capital M, and all surfaces are frictionless. Of course, gravity acts downwards. Before we start doing anything, how do we approach this problem? Let's look at what the problem wants. We need to find the time it takes for the block to reach the bottom of the plane. So we have to find the position of the block as a function of time, and the time at which that position reaches the bottom of the plane, that's the time we want. Now, in order to find the equation of motion, we can use Newton's second law straight up, but this is a pretty complicated system with the block and the wedge, so it's probably best to use Lagrange equations. In order to use Lagrange equations, we need to set up our coordinate system. The motion of the block is down the inclined plane, so we can set up the position of the block as q1, which starts at 0 at the top and increases as we go down the inclined plane. Meanwhile, the motion of the wedge is horizontal, so we can set up the position of the wedge as q2, which increases in the positive x direction. That means q1 of t represents the position of the block relative to the top of the wedge, and q2 of t represents the position of the wedge. So we have the coordinates of both of our particles. Let's construct the Lagrangian. The Lagrangian of this entire system is the total kinetic energy minus the total potential energy. We'll start by looking at the potential energy. The wedge is already in contact with the ground, so its gravitational potential energy is 0. The block's potential energy depends on how far it is above ground. If the block has advanced a distance q1 from the top of the wedge, then that must mean that it's gone down a distance of q1 sine alpha vertically. Therefore, the vertical height of the block relative to the ground is L minus q1 times sine alpha, because L sine alpha is the total height of the wedge. This means I can write my potential energy as mg times L minus q1 sine alpha. What about the kinetic energy? In this case, we have the kinetic energy of the wedge, which is just 1/2 capital M times q2 dot squared, plus the kinetic energy of the block, which is 1/2 mv block squared. The kinetic energy of the block is a bit more tricky because we don't quite know how to express the velocity of the block. So let's go back to our figure. The easiest way to express the velocity of the block is to go back to Cartesian coordinates and write the velocity of the block in terms of the velocity in the x direction and the velocity in the y direction. The velocity in the y direction is just q1 dot times sine alpha, but the velocity of the block in the x direction isn't just q1 dot times cosine alpha, because this is just the velocity of the block relative to the wedge. In this problem, the wedge is free to move at a velocity q2 dot, which is why we need to add the velocity of the wedge to vx to get the velocity of the block relative to the ground. So that means the total kinetic energy of the system is the following, and if we plug in the values for vx and vy, here's what we'll end up with. We can expand out the last term to get this expression, and then using the fact that sine squared plus cosine squared is 1, we can simplify our expression for total kinetic energy to finally get this. So now, after all this work, we have the final expression for the Lagrangian of our system. This Lagrangian has two coordinates, q1 and q2, so in order to determine the equations of motion of the system, we need to solve two Lagrange equations. One Lagrange equation for q1, and a second Lagrange equation for q2. Let's now solve these Lagrange equations, starting with q1. On the left-hand side, we're taking the partial derivative of the Lagrangian with respect to q1. The only term that contains Q1 in the Lagrangian is the potential energy term, and if we differentiate that, we'll get mg sine alpha. Now this is equal to the derivative with respect to time of the partial of the Lagrangian with respect to Q1 dot, and we can calculate this partial derivative. It'll turn out to be mq1 dot plus mq2 dot times cosine alpha. If we differentiate this term with respect to time now, we'll get mq1 double dot plus mq2 double dot times cosine alpha, and this is our Lagrange equation for Q1. We can't solve this without the Lagrange equation for Q2, so let's work on that. For the left-hand side, the Lagrangian doesn't contain any terms in Q2, so the left-hand side is just 0. For the right-hand side, if we differentiate with respect to Q dot, we'll get the following. Now, instead of differentiating the right-hand side with respect to t, we're going to integrate both sides because the left-hand side is just 0. When we do that, here's what we'll get. K, the constant of integration, equals m times q2 dot plus capital M times q2 dot plus m times q1 dot cosine alpha. Let's isolate the q2 dot in this expression. And once we've isolated q2 dot, we can then take its time derivative because that's what we have in the q1 equation. And when we take the time derivative, here's what we'll get. And now we're ready to plug this into the q1 equation. We can cancel the m's from both sides and then isolate q1 double dot. When we do that, we'll get this. We're almost done. In order to find the equation of motion, we'll have to integrate this q1 double dot twice with respect to time. When we integrate once, we'll get the velocity of the block, which is g sine alpha over 1 minus m cosine squared alpha over m plus capital M times t plus v naught, where v naught is another constant of integration. We know from our problem statement that the block starts from rest, so when t is 0, q1 dot is 0, and therefore when we do the algebra, we'll find that v naught is 0. We can integrate again to finally end up with our equation for motion of the block q1 of t. d naught is another constant of integration, but again the particle starts from the top of the wedge, which represents q1 equals 0. So at t equals 0, q1 is 0, which means that if you do the math, d naught is 0. So this is our equation of motion for the block. Now we can answer the question, at what time does the block reach the bottom of the wedge? Well, we know that at the bottom of the wedge, Q1 is L, because L is the length of the inclined surface of the wedge. So all we need to do is substitute Q1 equals L and find our time. I trust that you can do the basic algebra and isolate the time, which will turn out to be the square root of 2L times 1 minus m cosine squared alpha over m plus capital M, all over g sine alpha. And this is the time needed for the particle to get to the bottom of the wedge when the wedge has a finite mass and is free to move on a horizontal surface. So that's it. Congratulations, you've solved a physics problem requiring the use of Lagrange equations that would have been very difficult to solve using conventional techniques. Anyway, that should do it for the video. I'd like to thank the following patrons for supporting me at the $5 level or higher. I've linked my social media pages in the description for you to check out, and if you enjoyed the video, feel free to like and subscribe. This is the Faculty of Khan, signing out.